So good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. So we see each other again. Share my screen. Share screen. Um, okay. Very good. Now we are now in the chapter 4. So in the previous 3 chapters, we have learned a little bit on introduction on the refinery, and then the second one is on the mathematical optimization or process optimization, and then the last week we discussed on the some unit operations, and then how we can use process simulation software to do to get the data, and then make some regressions, and then use that regressions models into for optimization. Yeah, and then that becomes the like a procedures of the case study for the project that you guys are doing. And then for today is more on so we look at the plant as a whole, but in this case from the hydrogen perspective. So there are very good references over here. So I would like really encourage you to see and so to really get or read these 3 papers. It's very easy to read, and also it's very interesting as well. Let's give some like theoretical or fundamental aspects on the hydrogen, and then how it is being used in the plants, and then some potential or opportunities that we can use. Yeah. So before we go any further, so we have here like in one of the books, it's like they call it like modern refinery. So I put this diagram again. I think we have seen this couple of times already. So we have the crude oil coming in through a series of heat exchangers, and then desalting unit, and then another series of heat exchanger, and then a heater somewhere here, and then it goes to the atmospheric distillation unit, where it splits to naphtha, kerosene, distillate, gas oil, and then the residue, and then the naphtha, for example, in this case, the heavy naphtha, it goes via hydrotreating, what they call hydrotreating. So it's the goal of this unit, as we discussed last time, it's just simply to remove the impurities before it goes to the catalytic reforming unit, where the catalyst is very prone or very sensitive to the impurities. So in this case, we need hydrogen, because that sulfur, it will become like a H2X, H2S, and then we also remove nitrogen and then oxygen in this case. So we have also like a hydrogen desulfurizations over here. So we need also hydrogen to desulfurize some of this. In this case, middle distillate. Right? Middle distillate goes here. So we desulfurize the hydrogen. So we have like an arrow coming in. So it's arrow also coming in for hydrogen. Um, and what else? Yeah, I think these two, and then so we have hydrogen coming into these two boxes, and then we have also like hydrogen in here. So we discussed last time about the catalytic reforming, where it also produces hydrogen. And then, oh yeah, catalytic hydrocracking is also requiring hydrogen. So in this case, we require hydrogen to do catalytic hydrocracking. So we discussed this last week as well. So we have in this particular diagram, we have like 3 boxes requiring hydrogen, and then one box produces hydrogen. So what's not seen typically, we have like an hydrogen plant somewhere, where that hydrogen plant is hydrogen is produced via steam reforming of methane. So we'll go to that. So up until here, these are like typical locations and then typical usage of hydrogen. So we call it like hydrogen consumers and productions. Um, So hydrogen consumers, so like I mentioned before, so it's hydrotreating process, hydrocracking process, and then you can calculate basically how much then hydrogen required per ton of it if you know the concentrations of impurities. So from the mole balance, you know exactly how much you require. And then the same goes with hydrocracking process. If we know the feed characteristic, and then we know what kind of products that we want to produce. So from the mole balance, you can calculate that as well. So I showed you that on the other day. For both of these two processes, the hydrogen is required at a high pressure and then at certain purities. And then the hydrocracking process, typically it requires a higher pressure than the hydrotreating. And then the heavier the feed, typically we will then use higher pressure to simply remove the impurities, and also to to get like the hydrocracking process runs towards our need. And then um, as we saw last time on the hydrocracking, that hydrocracking process is a typical like hydrogen consumer unit operations. Yeah, because it's hydrotreating, and then hydrocracking. Um, so we have like in this case we have like a hydrogen makeup. We have feed first. We have feed, and we have hydrogen. So feed and then the mix with hydrogen. So they go to like a series of preheater and then like a heater, and then it goes to the reactor, where in this reactor we have like a catalytic reactor. So there are different types of reactors. We're not going into detail for that, but in this case you can see it's like a fixed bed reactor. So if it's a fixed bed reactor, so the feed is typically like a light feed. Yeah, a light feed. It's not going to be like we're not going to do like a relatively severe reactions in the reactor. So that means the fixed bed catalyst typically can handle that. And then because it's a high pressure and then high temperature, and then we cool it down a little bit, and then we separate that into the separator. So this is what we call like higher pressure separator, high pressure separator. So we have like a sour water, maybe also have some water to wash, and then the light gases is then going up. Yeah, light gases is going up. So that light gases contains lots of hydrogen, as we saw last time. So it contains hydrogen, and then we have in this case, say for example, in this case it's like hydrotreating. So we have a like a sour gas over here, right? So it's a H2S. So that H2S is then removed by lean amine, and then so this guy is then go together with the H amine, go to the regenerator unit somewhere here. Yeah, somewhere there, and it goes back. And then the higher pure the purer gas is then some of them is then recycled, and then some of them is then purged, and then purged and then recycled. And then the one that's recycled, obviously, where the gas is then undergoing the whole series of unit operations, there are pressure drops everywhere. So this compressor is then used to make up for that pressure loss. So in such a way that this pressure is about the same as that pressure, make up hydrogen pressure, and then it goes back here. So obviously, hydrogen coming here should be the same as hydrogen going out there, plus the hydrogen required for the reaction. Yeah. So that's obvious. And then the heavy part, or the liquid part from the separator, we typically we have another like how to call it, like a low pressure vessels, or then there's some valves to reduce the pressure in such a way that this distillation column typically operates like a close to ambient, or close to atmospheric pressure, where we have the gases, and then we have some in fact we have some outlet as well, and then this treated product as well is then going to it goes to different units. So it could be like the treated products are over here, and then these are the heavies, which is then recycled back like we saw last time. But this is then the typical the hydrogen. So the idea of this diagram is then to simply show you the hydrogen flow. It goes here and then it goes there. So here, there, goes here, go back here, and then the other one goes there. Okay, any question? No? Now, how about the hydrogen producers? They're typically like two unit operations. We mentioned this already. So the first one being like the ones that we have typically in the plant. So the reformer units. So in this case, it's it uses the latest technology, which is then continuous catalytic reforming unit from UOP, and then where it produces hydrogen, lots of it, but it's at low concentrations of hydrogen. And then compared to that, we have like a steam methane reforming unit where we mix steam, which is obviously water, right? So we mix steam, H2O, and then there's methane, so it's a methane, so it's as simple as that. So hydrogen plus methane, that makes what we call like a syngas, so CO plus hydrogen. Yeah. So in this case, you can do like a mole balance, and then we have like a 3 hydrogen over here. So using 1 mole of methane and then 1 mole of hydrogen, you could produce 3 moles of hydrogen, so which is a lot. So this unit is now the workforce um, of the what we call now. This is then basically the hydrogen plant, yeah, the hydrogen plant. So the hydrogen plant in the refinery, because it generates lots of hydrogen, and then we can, and as part of the plant, we can make it like a higher purity hydrogen as well. So the typical process for this steam methane reforming is something like this. So we have a natural gas. We have natural gas over here. So we heat it up simply, and then we remove some sulfurs whatsoever, and then we mix it with steam. Yeah, and then it goes to this reformer, and we have some fuels, and then the outlet of this unit is then here, goes there, and then because it's at high temperature, it generates some steam, and then the remaining is still at like a higher temperature, and then it undergoes the first step. Oh, I mean the second step, the first step after the steam methane reformer, where it undergoes what they call like a high temperature shift reactor. So because it's still a high temperature, even though it generates steam already, but this temperature is still high. This the goal of this unit, so this one unit, high temperature, and then this also low temperature. So the goal of this unit is simply to maximize the productions of hydrogen. Yeah, simply maximize the production of hydrogen. So we will see the reactions after this. Um, so number one is then to simply speed up the reactions, and then while it is still at a higher temperature, so it makes sense to put this high temperature reactions upstream, and then the low temperature reactions downstream, and then they then remove the gases, and then remove the heavies if any, and then there's the CO2 removal. And then if you have like some CO, and then there is this some methanation happens to make methane. So we need to remove CO to make like a pure hydrogen. Yeah, I mean, having this methanation is also consume hydrogen, yeah, because CO plus hydrogen, we make methane, and then in that sense, we are losing some hydrogen. So it's very important that in these two reactors, because the goal of these two reactors is then simply to react CO with that water to make more hydrogen. So we need to minimize CO as much as possible at this point. Okay. And then this is more another option. So they have the same thing. So natural gas and then steam. Natural gas is then being desulfurized, and then it goes here, and then goes into the reformer. The outlet goes used to generate steam to get the heat, and then there is only like a high temperature steam, high temperature shift reactions, and then some PSA unit, so pressure swing absorption unit, where it separates the hydrogen from the gases. and that gas is then being used again as fuel in this case. So that's basically the same. I mean, well, the basic concept is the same. It's just like different technologies. They will then they're able to produce a different purity of hydrogen. So in this case, for example, with the PSA unit, they can create like 99.9% volumes of hydrogen. In this case, they have like 98% volume. So uh, and the reformer itself, it typically it uses steams at 800 degrees C, 20-25 bars, and then with this catalyst nickel or alumina. And then we have like a steam to carbon ratio of 2.5 until 5. The reformer inlet temperature is about this, and then the reformer outlet temperature is about it's about 300 degrees C higher. And these are the typical reactions that we know. I mean, if you go for textbooks, they use this kind of reactions, but there are a lot more some minor things that we don't know. I mean, we don't have it here. So the main reaction is this guy. So steam methane reformer. So it makes CO plus 3 hydrogen. So it's really, in this case, it's really endothermic. Yeah, it's really endothermic. So 200 kilojoule per mole. Um, and then we have also this is then this is then the water shift uh, the water gas reactor. So we have the water, and then we have the gas. Yeah, the water gas reactor. So so it generates the CO2 and then the hydrogen. So in this case, um, um, this is like an equilibrium reaction. So depending on the temperature and pressure, so it can go to the right, it can go to the left. Yeah. And then that's then the use of the previous high temperature shift water gas shift reactor and a low temperature water gas shift reactor in such a way to make sure that we have enough we reduce the CO as much as possible, and then we produce hydrogen as much as possible, yeah, in that case. So these are I put this I took it from from one of the textbooks. So it's a typical feedstock composition into the reformer. So if we have like a methane, so this methane is about the outlet compositions of a reformer. If we use like a methane, so if we use like a methane, so majority is then methane. So that methane is then going to be converted into the syngas. So we have 12% of CO and then 75% of hydrogen. And then if you have like a natural gas, so natural gas is not as pure as methane. Yeah, so there are there's lots of CO2 as well. So depending on the natural gas composition, so it can typically generates in this case it generates this kind of composition. Outlet compositions, if we have like an LPG, so we could also use LPG, C3 and C4, and then obviously because it's C3 and C4, we produce a lot more C components in this case than CO and CO2. Yeah, but then we have like about comparable concentrations of hydrogen, but then um, and then if you use like naphtha, so obviously naphtha is on the heavier or on the it's a heavier than LPG. So we have a lot more C in that stream. So we then create a lot more C as well in the outlet. So we then CO and then CO2. And then if we see here, so the hydrogen concentrations, if we the heavier we go, the lower the hydrogen outlet concentration. Yeah, lower the outlet concentration. Simply because the feed itself, it contains already relative to the C, it contains already lower hydrogen. Yeah, if you understand. So because if we have like a methane, so we have a methane coming in. So we have C and then 4H, right? But if you have like an LPG, yeah, it's a C3, say C3. So how much is then the H? Anybody can tell me? Huh? It's 8, yeah? So we have it comes 3C and then the 8H. So in this case, you can then see the H over C is then 4. And then while in this case, H over C is 8 divided by 3, which is then, 2 something, right? 2 something. So in this case, you can then see why. Uh, a minute, yeah. Minute. Now my the screen is doing um, um, where was I? Yeah, here. Okay. So this is then the water gas shift reactor reaction. Sorry. So we have like CO and hydrogen, CO and water. Um, and so we have water and then we have the gas. So that's what the gas shift reaction. So they shift it to the right or to the left, basically. So it's the goal is then, like I mentioned, it's to produce hydrogen as much as possible. This is equilibrium reactions. So depending on the operating conditions, you can direct where it goes, and then it's moderately exothermic, so it's minus 41 kilojoule per mole. And then according to the research, they say, well, because at lower temperature, the reaction is not fast enough, so you need to speed it up the reactions by increasing the temperature, right, from the Arrhenius constant. So in that sense, below 250 degrees C, if you increase the temperature, goes up, you will then produce a lot more hydrogen. So the reactions will then go to the right. But then after that, it will then go into that closer to the equilibrium reactions. So at higher temperature, at higher temperature, that means they utilize the higher temperature in such a way that it will then produce as much, or the reaction rate goes as fast as possible. So they have like typically they have like this iron oxide and then chromium oxides as the catalyst, and the temperature is about 300 to 400 degrees C. Okay, so remember that the outlet temperature of that reformer, yeah, somewhere around here, it's about 800 degrees C. So they generate the steam, right? So they generate the steam in such a way that the outlet temperature of that steam generator is about this number, so 300, 450 something, or 400, and then they go and then they put it into this high temperature reactor to go to produce hydrogen as much as possible. Then they reduce the temperature, it goes to the low temperature reactor. So this it has a different catalyst. The copper is then the active site, and then temperature is reduced to 200 below 250 degrees C, 200 to 250 degrees C. If it goes below 200 degrees C and then there is no reaction, I mean the reaction shouldn't be very slow. So they maintain it in between this temperature range in such a way that um, that the productions of hydrogen can still be maintained, or this CO can be minimized as much as possible. Okay. Any questions so far? Yeah. Okay. Now we have the so in the refinery itself, we typically we have so you took this from one of the articles as well. So we have like a hydrogen balance, so in that refinery. So if we make a hydrogen balance, so if any of you you're using hydrogen in your plant, and then try to make a hydrogen balance, then to see whether you have enough, or you have oversized capacity of hydrogen, or you pay a lot more hydrogen. So this hydrogen balance typically this hydrogen import. So this one is typically what we call from the either you import that, or from the hydrogen plant if you want to design the hydrogen plant. So in this case, so it imports hydrogen, and then the concentration of hydrogen is about 92% volume. So 92% volume, and then the flow rate of hydrogen is about 45 million standard cubic feet per day, million scf. Okay, and then we have another source of hydrogen, which is in this case the CCR, the reformer. So the CCR itself produces 23.5 million scf of flow rate, and then the 75% of that is hydrogen. So we have like in this case two sources of hydrogen, and then it goes to some pipelines and stuff, and then it ends up into the hydrocracking catalyst, hydrocracking unit. And that hydrocracking unit, in this case, if you can see, So it requires like 38 something million scuff, and then the concentrations required in this case, if you can see the gram, it's 92%. So this one is 92%. So we need to have like 92% from this diagram. Yeah. And then after that, there is a hydrogen connection here and there, and then this kerosene hydrotreater. So apparently this guy they need like 8 something million scuff of fluoride, and then 75% of kerosene sorry 70% hydrogen concentration. So this hydrogen concentration is coming from the hydrocracker unit, so it goes straight. So the same goes with CN. Yeah, maybe I don't know. Maybe it's something. I don't know what this CN means. Oh, see. So cracked naphtha. So cracked naphtha hydrotreater, and distillate hydrotreater, and then this then the naphtha hydrotreater, and then this then isomerization unit. So that's how you read these the numbers here. And then the rest of this hydrogen, I mean the outlet of this kerosene, the naphtha, and then a lot more from the CCR unit, they go to fuel system to be burned, yeah, to be burned. But then if we see this diagram, because this is what you typically see here, so it goes, for example, just get this hydrocracking unit again. So it goes like 38.78 million scuffs into this hydrocracking unit with concentrations of 92%. So it tends to I mean you would think that this hydrocracking unit it requires 38.78 million scuff at this 92.7 at this 92% volume. That's what we normally think if we see this kind of diagram. But is it really true? Is it really true? Because as you saw, typically we have this kind of hydrogen line. Yeah, we have the makeup line. So this the one makeup line is then the 38 something, and then the 92%, 92%. Yeah, but is this the what is really required? So what we if we zoom in, yeah, so we have the hydrogen consumer typically. For example, in that case, it's the hydrocracking. So we have it has like a liquid feed, and then we have the makeup hydrogen, in this case 40 million scuff, and then the 99% of hydrogen. So it could be coming from the hydrogen plant. And then if we have that unit as a black box like this, and then where we put the boundaries, and then we draw in and out streams, which we have to do for all kinds of unit operations in our plant. So we will see there is like a high pressure purge, 15 million scuffs with these concentrations of hydrogen, and then there's a low pressure purge, 5 million scuff, 40%, and then we have like a liquid product. And then if we zoom in here, so we will see this kind of diagram. Yeah, see this kind of diagram. We have liquid feed, we have the hydrogen makeup, and then we have the purge. Right, this is then the 15 million scuffs with the 80%, and then we also like the low pressure purge, the 40%. And the one that is being recycled is then the one that is from the high pressure separator. Goes to the recycle and then mix with the makeup hydrogen, and this we know that this purge reactor, purge reactor, that this concentrations over here is the same as concentration in the purge, and then which is then the 80%. So we mix the 80%, 200 million scuff of it with the 99% of 40 million scuff of hydrogen. So in the end, if you calculate this, you will get like about 83% of hydrogen being recycled or being fed into the reactor. So we don't need apparently the 99%. Yeah, we don't need 99%. What we need basically is 83%. So in that sense, it gives us like a kind of like an opportunity. Okay, so in that case, we may not, I mean, it's something that we can play around, right? It's something that you can play around. So this insight is being used in what we call the hydrogen pinch, things that we're going to see in this lecture. So based on this definition, I mean, based on these situations, basically, based on these situations, um, um, based on these insights, basically. So they defined things like a source and sink, or source and demand. Um, So source means like a source of hydrogen, yeah, source of hydrogen, and then sink is also like a sink of hydrogen or demand of hydrogen. So if we look at this, they define it like the source is then the one that goes from the first separator or the separator, things that before you go to purge and recycle. So this is then the source. So before we do anything, so before we know how much we're going to purge or before we know how much we're going to recycle, so this stream, the flow rate, and then the hydrogen concentration is then the data of the source stream. And while on the other case, on the other hand, we have like hydrogen required, right? The hydrogen required is then this point. So the hydrogen required is that it's not the hydrogen makeup or it's not the hydrogen recycle, but at this point. So the flow rate that we need, or the flow rate that goes, yeah, the flow rate that goes to the reactor, and then the concentrations of hydrogen that goes into the reactor, this is then the sink condition. So this is the data that we need to obtain from the plant. And it's also that this is then the data that basically we need to supply into the reactor, not the conditions of the hydrogen makeup or the hydrogen recycle. So from here, if we know then the amount of hydrogen makeup concentrations, if we know how much is then the purge and then the concentration, and also if we know typically how much is then the hydrogen recycle because it goes via a compressor, so we have the flow rate of that compressor. So then we can calculate how much is then the flow rate and then concentrations of hydrogen in the sink, and then the flow rate and concentrations of hydrogen in the source. So so do we have any questions on here? No. So now I want to.
Can I ask one question?
Yeah.
This is just a general question. The flow rate is basically the volumetric flow rate, is it, or mass flow rate? Because I think
up to you. But typically we have like a million scuff. So that million scuff is volumetric flow rate. But since it's already at like standard condition, right? It's a standard cubic feet per day. So because it's at standard conditions, I don't remember standard condition means like 0 degrees C or 25 degrees C, something that we can Google quickly. Yeah. So at standard conditions, so that means it is correlated to the molar flow rate of the gas.
I mean that if you want to do the mass balance, can you use this millimeter scuff?
Yeah.
Because mass flow rate is mass, right? This is volume. It's the same.
Yeah. You can use that volumetric flow rate.
I see. Okay.
Yeah.
Right. Thank you.
Very good. So now, since you asked it, now let's calculate. So how many of you know? All are in or no? So we have 1, 2, 3, 4, 5. Oh no, 5. 1, 2, 3, 4, 5. Yeah. So we have a makeup data, so we have a purge data, and then we have a recycle data, like I mentioned before. So now, if we go for the diesel hydrotreating, so diesel hydrotreating, diesel hydrotreating, goes to, so we have like a source, and then we have a demand, instead of sink. So source, how much is then the flow rate? How much is then the flow rate? How much is then the concentrations of hydrogen? I put Z. Now who can tell me? Or should be one. I cannot see who's who. Yeah, when I'm in full screen. So now for diesel hydrotreating, how much is then the required flow rates into the system? So this one should be very easy. Anybody? The concentration. Flow rate. How much is the flow rate? As the source, you can see. So this is then the source. Source. This is then the sink or demand. using also. So source and sink, source and demand. So the source flow rate, how much is that? Anybody? Come on. I know that this is late. Saturday afternoon. Now the brain is frozen already. So I'll help you. So we have the purge data, no? So we have the purge data, we have a recycle data, and then source is basically purge plus recycle, right? So purge plus recycle for diesel hydrotreating. So purge plus recycle. So how much is that? So yeah, 10 something, right? So it's about 10 something. Am I right? 10 something million cost, right? And then concentration. What's the concentrations of the source? These concentrations. What's the concentration here? Okay.
70.
70. Yeah, exactly. 70. So 70 is then the concentrations of the source. So we have done with the source, right? You will need this, yeah. I think this goes to the test, no, Afik.
Yes. For test we cover hydrogen.
Right. So this is the yeah. I always tell the students what kind of exam questions they will get. So the right. So and then the demand which is then the sink over here. So we have so how much is then the flow rate? Anybody? Flow rate to the demand. Flow rate to the demand. Flow rate of the demand, which then goes to the reactor. Flow rate of the demand streams for this desired thing. Okay, I will help you.
Let's recycle.
Yeah. So we have the recycle and we have the makeup. So simply this then makeup plus recycle. So makeup is then the 11 and then recycle is 1 point something. So it's about 12.8 something, 12 point something. And then now comes it's not that I mean well it's straightforward, but you will need more brain power. So what is then the concentration of hydrogen here? Concentration of hydrogen here. Yeah? So it's not simply addition. No. Um, right. So you have the hydrogen makeup flow rate. You know the hydrogen concentration flow rate, and then you have the hydrogen recycle flow rate, and then you have the hydrogen concentration of the recycle stream, and then calculate the hydrogen concentration in the demand stream. So what to do? Huh? Anybody?
Times the flow rate times the concentration, and then add up.
And then go on.
Yeah.
Go on. A little bit more. So we have makeup, right? So 11.
The total flow rate.
Yeah, exactly. Time 11 something times 75 something plus the recycle at 1.56 times 70 times and divided by the 12 something. So you get your hydrogen concentration. Now. I don't know, yeah. This is out of my control, guys. So excuse me for that. So it's not really professional, but nonetheless, we'll see. Yeah. Okay. And then we have so with the same method, you can then calculate how much is then the source stream and then the demand. I mean the source conditions and the demand conditions for all of these units. So each of these units, it has its own source stream, it has its own demand stream, right? So you can tell. And then if you so these 1, 2, 3, 4, 5, 6. You can see that here. So 1, 2, 3, 4, 5, 6. So the only unit in this case that don't have a demand, that don't have a source stream is the isomerization unit, because it's the hydrogen is then purely consumed. There's no purge whatsoever. There's no source, um, and then you can see now. Yeah, I mean, using the same insights, you know that for sure that the source, sorry, the demand stream for the hydrocracking unit, for example, it's not 38.78 and not 92% of hydrogen as well. So it is something else. Yeah, that's something else. We can only tell if we know the purge stream. So it has to have a purge stream, and then it has the recycle stream, which is not shown here. Yeah, so it has the purge stream, and then the purge data if you go to the plant, and then we have the recycle stream and the recycle data when you take it the data from the plant. Oh, sorry, it has this purge. Oh, I know. I don't know what this streams are. It seems like it's not going to purge, because purge typically it goes to the flare. But in this case, it has like another line going to the kerosene hydrotreater. So it could be the purge, it could be something else. So it's something that we have to look into detail, how the hydrogen streams are connected into the in each of these units. Now, we have now, yeah, to go. We have the hydrogen plant, and then we have the reformer as a hydrogen supply typically. Okay. So how do this, what they call the so-called hydrogen pinch study? So they number one, obviously they do the mass balance like what we just did, and then they calculate the actual source streams and then the actual demand streams conditions, the conditions of both the streams for each of the hydrogen consumers and hydrogen producers. And then they will then do what they call like, yeah, see how much what we can do. What we can do means they look around and then see what they call like a low hanging fruits. And then they do like low cost modifications like a piping, and then I will show you. I mean, we will go to that. And then number three is then so there are like four steps. It goes with the complexity and then also capex. So it's all about money. So the more complicated it is, the more money that we have to spend. So they start from the very low end, so we can then fine tune something. So say for example, yeah, and then we have this purge. Yeah, I mean, why do we have such a purge, right? So we can just why don't we just close this down? So we close it, and then everything is then being recycled. Why can't we just do that? Yeah, something that you have to ask. Something that you have to ask always. Yeah. Well, there is no obvious answer for that, but then something that you have to ask. Yeah, why to have such a high flow rate of purge? Why not? Why can't we just reduce it a little bit more? Yeah, because reducing that will save you lots of money. And it's something that we have to always challenge the current conditions in the plant. But to challenge that, we have to have the knowledge. And then and then if then do something repiping, if we can reuse, because in this case, for example, so we only need, for example, in this 83%. So if there is any 83%, if there is any 83% of stream, yeah, the 83% or 85%, I don't know. So you can just simply that instead of having 99% of hydrogen makeup, so we can just remove this and then put this, the cheaper one, and put it here. Yeah. So if this is enough, yeah, I mean, because from the hydrogen perspective, that hydrogen concentration and the flow rate may be sufficient, but then in terms of the other impurities which we don't know, is something that we have to elaborate, something that we have to dig deeper. If that is also not an issue, yeah, all the other components not an issue for this catalyst in particular, and then you can then propose this as one of the modifications. So then you will then save this amount of money, right? So it's something that we can think about, and then something that we can then use as a base for a discussion going forward. Um, and then that's about this piping stuff. And then if you want to, like for example, well, we cannot just repipe it to somewhere, but we need to have like a new equipment, like a new hydrogen plant. So then the question is then how big is the new hydrogen plant? Yeah, how big is that? There's something that we are going to do now. And then if we need like new compressors or new purification unit or whatnot. And then the last is then we process modifications. So in this case, and because adding things is easy, yeah, adding things is easy, but then can we do something in the reactor? Right? If suppose that if there is a new technology requiring a lot less of hydrogen consumed, because most of this hydrogen typically, yeah, this hydrogen is a huge flow. You can see here in this example. So it's a huge flow. It's 200 million scuffs compared to this 40 million scuff. And then I mentioned to you that the hydrogen balance, so the hydrogen coming in, this hydrogen is apparently is the hydrogen consumed in here, hydrogen consumed, and then hydrogen removed over here, and it's also hydrogen over here, right? So this 1, 2 plus 3 makes this hydrogen makeup. So that's basically what this is. But then you have a huge amount of hydrogen being recycled simply because to account, I mean, to accommodate for the requirement of hydrogen partial pressure, and then the how much is then the hydrogen required for the reaction, and also for the for that to clean the catalyst. For example, in hydrocracking, so we need to prevent the coke from happening. So in that case, we have to then have a high partial pressure of hydrogen to make sure that the surface, the active surface of the catalyst is always cleaned, right? So it always have to have this enough hydrogen so that it doesn't crack to become coke. So that's the goals of having huge hydrogen recycle. So we can then simply do something with the catalyst, do something with the operating conditions in such a way that we can then minimize the hydrogen recycle, minimize as well the hydrogen consumed. That will be great, but then they will then take a lot more research and a lot more things to be done. So hence they put this like a typically the something that you will do if we have something, or we have some time, we have some resources, or we have money. So that's one of the options. Yeah, one of the options. And then so that's the framework. This is then the framework. So we start simple and low, and hydrogen pinch. I'm not going to show you how to draw this. You can go through the three articles that I mentioned in this slide. So you can it's a fun reading. Yeah, that one I can promise you. It's not like really it's not really written like a scientific paper. I mean it is a scientific paper, but then it's written very nicely. One of the nice, I mean, some of the nice papers that I've read. Anyhow, you can learn then from that articles how to draw this, but it follows the same way with the heat integration. So if so you are now in this masters of process integration, so you I don't know. Some of you must have done the heat integration course, and then some of you may not. Like in this case, some of you apparently don't get optimization course yet somehow. So in that heat integration, it's about quantity. It's about quantity and then quality. So the same way here in hydrogen bench, we have the quantity, which is then the flow rate, and we have then the quality, which is then the purity. Yeah. So in heat integration, I repeat, in heat integrations we have the Q, right? The energy, and we have the temperature. So this then becomes the quantity, which is then the quantity of heat, which is then the quality. Yeah, the quality for something to be transferred. For that heat to be transferred is then the temperature. Yeah, temperature is the driving force for heat to be transferred. So in this case, purity then you also call the driving force, because you will need to have a certain purity to have these hydrotreating, hydrocracking processes going on. Okay, so they separate this into two, like in heat integration. So we have the source composite curve and then demand composite curve. So this is then the why we did these calculations. Yeah, why we did these calculations. So once you get the source and demand data, you will then make this graph. So for example, in this source and demand graphs, we have to make it like from the highest or from the purest hydrogen stream to the to the least pure hydrogen streams. So in this case, so you can see it's close to 1. So we can see this at like a hydrogen plant. So maybe this is then 99 point something percent, and then that hydrogen plant is about something like this. It's about, in this particular case, maybe 80 million scuffs. So that hydrogen plant producing 80 million scuffs of hydrogen with this 99 point something purity. Yeah. So that's what this line means. See what this line means. And then this is then the hydrogen plant, and then the next how do you call it, next stair is maybe this then the CCR, I don't know. Yeah, so that CCR, so it could be like a hydrogen plant, and then this could be like the CCR. So that CCR producing about, this is 60%, 70 something, 75%. Yeah, it's about 75% of hydrogen, 75% of hydrogen, and then the amount that it produces, the CCR produces from here, so it's somewhere here. So this is 80, so it's about 20, so 50, this is 200, yeah, 200, maybe 250, yeah, right, maybe 250, so 250 million scuffs of hydrogen streams containing of 70%, 75% of hydrogen, the CCR, and so on and so forth. So you have this, and then there's this one, and then that one, and then this one. So you have 1, 2, 3, 4, 5 sources of hydrogen streams, and then the same way goes with the demand composite curves, which is then coming from the demand streams. So yeah, this one I cannot then say how, what this is, but then for how much, and then at 80% concentration, so we can tell, we can see it if we have the data. So we have like 1, 2, 3, 4, 5. We have five demand stream, 5, and then the 1, 2, 3, 4, 5 as well, the composite, the source. So five source streams, and then 5 demand streams in this example. And then they for every of these concentration level, they just simply like add them all together. They make like what they call like composite curve for the hydrogen composite curve. So instead of a flow rate over here, so they have the flow rate of hydrogen, the same concentrations, yeah, the same value, but it's just like a flow rate of hydrogen. And then the hydrogen pinch, what they mean by hydrogen pinch is that how much is then this line, yeah, in such a way that if we then transform these two graphs into one graph like this red or this green, we will then have somewhere here which has like a zero flow rate, because it's then zero, yeah? So in this like a brown line, so it touches somewhere here, so somewhere around 70% something, so it has like a zero line. So this is what they call like a hydrogen pinch, and then the amount of hydrogen required to do this is this much, yeah, that much. And you can tell now the green one is then the original case. So for example, in this case, if you then add this graph, the source and then demand graph, these two conditions at the beginning, it'll become something like this, yeah. And then you reduce this hydrogen flow rate, yeah, hydrogen flow rate, you reduce it to the left, means, so that means in the end you will get something like this, about, I don't know, about 8 something or 7, 8 million scuff of hydrogen, in such a way that the whole plant, like this 5 units plus 5 units, the total, I mean, this graph will then touch the zero flow rate. So that's the hydrogen pinch. I think I have it here. You can see. So this plus is then the plus means surplus of hydrogen. Simply, how do we know it's surplus? Because in this region, so we have hydrogen at higher purity. So for the same flow rate, this flow rate, so about 70 million scuff for the same flow rate. So we have a higher purity of hydrogen. So this part is over here, yeah, it's over there. And then this area, for this flow rate, we require a lot. I mean, we require hydrogen pure hydrogen. So because this is then demand, right? The red is then demand. So this demand stream, it requires 80% of hydrogen purity, while the stream that we have over here is 75%, for example. So that's then the minus. So when it goes to the minus, it goes to the left like this. Yeah. So this one goes. This is plus. So this whole string is then to the right. So this is then that stream. So this one, and then this area is then over here. Yeah, this vertical line doesn't mean anything. It's just like a to add to make sure that it looks like a stair. I don't know. So this green one, if you can then see, and it's the same like that one. Right? So apparently we could reduce the amount of hydrogen, like I mentioned before. So we can reduce the amount of hydrogen coming from that hydrogen plant in such a way that it then touches this x equals to 0 line or the y-axis. So that's the hydrogen pinch. So in this case, just like that heat integration concept, it means that this is then the minimum amount of hydrogen, theoretically speaking, that we have to supply into the plant. Yeah, the minimum amount of hydrogen that we have to supply into the plant. Can we supply more? Yes, obviously you can supply more, but then you have to pay more, right? But can you supply less? The answer is not. Yeah, you cannot supply less amount of hydrogen than this number, than this 8. Yeah. So if someone tells you from your data plan data, and then they have like this technology or whatnot, and then they say, well, we can build for you, we can calculate this, and then we can build for you, and then the hydrogen capacity would be like 5. So it's a lot less than what you previously have, and you know how to calculate this, and then you can then tell that they are like lying or bragging or whatnot. Okay, because it's in terms of the well, thermodynamically, in this case thermodynamically, it's mass balance case. It's not thermodynamic like in heat integration. So here in mass balance case, you will never reach below this number, below this number. You can go more, obviously, but you will have to pay more. Yeah. I mean, also due to practical circumstances that we don't know, which is not included in the simple analysis. It may be like higher than this number. Well, for sure it will be higher than this number, but we cannot go lower than this number. So that's basically the pinch. I mean, how the pinch is then being interpreted. Okay. So this is then the first step. So we know the first step in this pinch analysis is that we know how much hydrogen, minimum hydrogen, that we have to fulfill, that we have to supply. Yeah, how much minimum hydrogen we have to supply. That's the first question that we can answer. Now the second question that we can answer is, in this case, if we have like a hydrogen purifier, for example, pressure swing absorber. So if we have that unit, yeah, somewhere, or we can use it, or we want to buy it instead of building a new hydrogen plant, where should we put it? In terms, not in terms of the location, but in terms of how, what is then the feed purity that we have to put into that PSA. Yeah, because let's say for example PSA. So we have the PSA, right? So that PSA, how much then how much the F, and then what is then the concentration, in such a way that we can then use it to the plant, right? So you have your plant, right? I don't know, it's very ugly. So your PSA. Question is that how much the PSA should be, and then at which concentration. If you don't do this analysis, and then you have this plant, for example, right? You have this plant, for example, and then like common people will then say, well, if I were to put, like, for example, I will need more hydrogen, and then I cannot import more, and then I don't want to build a new hydrogen plant because of, I don't know, I mean, capex limitation. And then you would say, well, if we can then design and buy a hydrogen purifier, or in this case PSA, for example, uh, where shall we put it? So, well, typically we can then say, well, we have this goes to the fuel system. So instead of going to the fuel system, so we have this PSA unit, right? So I have this unit, so we can just put it there, close this, and then put it over here as well, and then close that. And I have a big streams over here somehow. which I don't know why it goes here, so I can just put it there. Maybe it's so we have like a, because this line is 75%, right? 75% hydrogen. This one is then 60% hydrogen, and then this one is then 65%. So 65% times this, 60% times that, 75% times this. You can then calculate how much then the flow rate and then the hydrogen concentrations. And then the resulting hydrogen purity, hydrogen flow rate and purity, it goes to the to here, for example, right? So this is what people think if they don't know this concept. But then, is that really the case? I mean, is that really? It could be the case, yeah. It could be that that is then the correct solution, but it may or may not be the case. So if we see this, if we make this hydrogen pinch, and then what we could do is that so in heat integration you have learned something what we call like heat pump, right? So that heat pump is typical. I mean, it's the same concept in the as in the hydrogen purifier in this case. So for that heat pump is then you simply then to bring the heat from the below pinch to the above pinch. So in this case, hydrogen purifier is that we bring the hydrogen at the lower purity here below the pinch, and we bring it up. So we know that, for example, in this case, the concentrations. So if we bring this, so say for example, yeah, what is needed. But say for example, yeah, because this is all we have like for example, in this case, this is, yeah, I don't know. This guy is say for example 8. Oh, sorry, 7. I don't know. This one. So this one 5, for example. So we now have 5 million scarf of hydrogen. So so instead of supplying it at this concentration, we could then supply it at this at lower concentrations over here. But then we will need to have a more hydrogen, right? So and then you can then say, okay, now I want to say, for example, if I mix this stream, because this is then that lower stream, a low concentration, mix this stream with that stream with that stream. So you have like this amount of stream, yeah, this amount of flow rate, sorry, with a certain concentration somewhere in between, for example, somewhere here, somewhere here, and then this then the amount of flow rate of hydrogen with this specific concentrations. So then now you can then solve this and solve that in such a way that you can then put it into PSA, and then you know that, well, I can then I don't have to design at a very pure hydrogen, so I could design it somewhere here, and then some with a little bit more flow rate over here, yeah. So you will have to do recalculate the mass balance. So so with this, using like a somewhat in between concentration, so it's not very low, and it's also like producing not so pure. So you know that from the cost perspective, in this case, it will be then a more cost-effective solution instead of starting from here, from the if you mix everything and then the concentration here at the lowest point, right? At the lowest point, because at the lowest point, for example, in this case, if you put it in the same graph, so if you are then say, oh, now I have this stream here, as an example. So I have this stream at the 30%. So I want to pump this or purify the hydrogen from this temperature, from this concentration level up over here. So the amount of money that you produce over here will be much more expensive, much more expensive, instead of just from here to there, right? Right. So this is then the insights that you can use when answering the question, how big is then the PSA, and then from which to which concentration that we can then design the PSA. So again, before we go to the example, so the goal of this hydrogen pinch is in a nutshell is then to know what is then the minimum hydrogen that we require, at a certain concentration. And then the second one is that if we are asked to say, for example, in this case, if we have a hydrogen purifier, how big is it? How big do we need? And then from which condition to which condition shall we design it for? So that's the how it will then help you answer these two questions. Do we have any question? No. Okay. Case study. What time is it? Yeah, I don't have mine. Now, how big is the required hydrogen plant? Oh, okay, before we go to that, let's do this. Let's do this. Let's do this. So I have
Dr. Supan,
yeah.
there is some issue, concern regarding the scene 3, right? The example that you did last time. I think all of us cannot do because of the license issue. So I think for the project we need to think something else because the utility license did not cover the unit that you use.
Okay.
So yeah. So I think we need to think something.
Yeah, I've asked them. I think we discussed this in the WhatsApp group. So I've asked them to provide UTP with a full license, which is that 2 days ago, right? So they are already in vacation mode. So hopefully they will come back to us next week to give
You mean
you.
the ITMS?
Huh?
You mean the ITMS?
No,
Right?
the Islam budget.
Oh, the Islam J. Okay, they can give the UTP.
I'm asking them, and then hopefully they can, because I don't see any issue. Well, I don't see an issue, but then if they see an issue, that's something that we have to know. But well, the bottom line is that I've asked them being somebody to provide UTP with full license, simply to so that you get to know the Piona and the hydrocracking and the
Yes.
refinery models, right? So hopefully we can have the reply next week somewhere, because they are in the holiday mood already for the last 2 days. So it's something to be yeah, we'll see. Hopefully the reply will be positive. If it's not positive by next week, you can design, you can design, I mean you can model different process, yeah, not necessarily refinery, because for that refinery you need to have the additional license. So you can model a different process, but what I need is then you need to have like a reactor and then the distillation column. So these two units have to be there. And you can use I don't know, just go to I think if you go to a book called let me see, yeah, Turton handbook, Turton chemical engineering, this one. um, so you go to this one. You go to this book, Analysis, Synthesis, and Design of Chemical Processes by Turton. So in the appendix, I think appendix B or something, appendix B, there are many chemical processes that you can then use for the case. And then try to model that. It has also the kinetics, yeah, it has the kinetics. Try to model that into the reactor. So don't model the reactor as a conversion, because it will then because then you know already what the answer is. But then, but okay, I would say, I mean, for the sake, because if you model the reactor based on the using the kinetics, and then it has recycles in it, and then it will be, I mean, it will need more effort to converge this, and then when you want to run case studies, sometimes it may or may not. Sometimes it doesn't converge. So you have to do some tweak. So this tweaking requires a different set of skills. So which we're not going to elaborate here. So maybe you can then simply escape by using the conversion reactor, and then use the distillation column. So that at least we have the reactor and distillation column, and then you can then do whatever you want. Yeah, then do whatever you want, and then you can then assume that conversion is then one of your independent variable, right? And then that conversion obviously depends on the temperature, which well, you have or you don't have it, but then it's something that you have to think. Okay, so what I want to know is not the correctness of the results. It's what I want to know is then how you think to solve that this kind of problem. Yeah, that will be our backup plan. Hopefully, by next week they can give us the full license. If not, then we will use this backup plan. So this is just an example. Yeah, you can go Google, you can Google all kinds of processes, and then develop the model in symmetry, and then do the sensitivity analysis, and then get the data like I showed you yesterday or last week. And if there's any question, or if there's anything that you want to discuss, please let me know. So because we have the WhatsApp group, right? And so far I don't see any remark or question. So I assume it should be okay. But but apparently not. It's just like people being silent. Unless anyhow. Any good, very good. Any other question or remark or suggestion? Anything? No? If not, then I have this in one of these think here. So I opened the article already. Hydrogen pinch. So in here, I don't know if you can get this article. I get it somewhere because this was like a long time ago, 2008. So this from this article, they developed like a VBA based Excel file where they can then say so they use, like in this case they use GoalSeek, and they develop this Excel, and then this Excel is somewhere. You can download this, or I can just share it with you, but I'm not really sure if what I have is still working. We can just simply see. GoalSeek. One minute. Where is that link? I don't know. It should be mentioned. I mean, I may miss this, but if you have these articles, then you can then find where they store it, or maybe you can go to the because this professor, it has like its own web page, so you can go to his web page and look it up there. But nonetheless, it gives us something like this, yeah. So it's something like, so we have the data, the one that we have been talking. So and then they put the data here. So see, you can see. Can you see? Let me know if you can see. So they have this hydro cracking unit in, and then means the this one, yeah. If they say it's in, means this is somewhere here. Where is that stuff? A minute. Oh, so if they say in, that means it's here, the demand. And if they say out, that means this the source. Okay, so the demand is in, so which is then the sink. So here the demand stream is in. So hydrocracking and naphtha hydrotreating, distillation, and then crack naphtha. So they have these namings, and then they know what is then the molar flow rates for the demands. You calculated that already, and the required hydrogen concentrations over here. So these two columns. The same way we input the data for the source. Like in this case, we have the import gas, and we have all of these sources, yeah, which you calculate already, and then the flow rate, and then the concentrations. And then they will do what they do here is that they use GoalSeek in this case. So they change D17. So this then D and 17, which is then here. So in this case, they want to set this number to be 0. So they want to change this number by changing that. So they change this number. So this import of hydrogen, they want to change this number in such a way that cell N26 becomes 0. So N26 is N, and then 26 is somewhere here. So this one, this becomes 0. Why they need this to become 0? If you see all of these numbers, this is then the closest to the 0 value. So you can where's my information?
Does it mean we want to shift it?
Yeah, exactly. So that
Okay.
the two something, sorry, this two something is this basically. So they want to, so this is not touching the x equals to 0, yeah, it's not touching that one. So like I mentioned, so we need to reduce this, the pure hydrogen or the import hydrogen, in such a way that the whole graph will then move to the left, and such a way that this is then being touched. I mean, it touches the this y-axis, and then we have to see, because this is based on the goal seek, so we have to see where this thing is located. So for example, in this example one, so it's in the in n 26 or n26, the first one. So the first one, yeah. And then if we go to the next example, think, yeah, next example. Oh, this is the example one. And next example, example two. So example two, they want to minimize n26 again. N26 is somewhere here, right? So 26. This one is 1.2, which then oh, this is not the smallest one, so I may misunderstood this, but they for sure that will then change the hydrogen flow rate, the D19. So let's see, to reduce the cumulative hydrogen surplus of 1.2 in cell 26, which is example 1. 1.2. Let's see. Oh, it's strange. I mean, I see. Yeah, you have to read this. Yeah, I mean, I also need to read this. Yeah, let's see. This is. So they have this analyze button and stuff. A minute. Let's see if I can still. Surplus weight of 2.9, which is that one, in case example 1. Right, so figure 3, in figure 3, this one, this is that the 2.09, and then case 1. Okay, now so now case 2, if you go to case 2, to reduce the cumulative hydrogen surplus, okay, cumulative hydrogen surplus. This is very strange, not 1.2. Anyhow, there's something that you have to play around. I mean, just read this, and then I'll share you with the I'll share you, if you cannot find it. I will just share you the Excel file. Yeah. So that Excel file is it looks something like what is then shown here, like this one. So they have can you see? Can you see? So they have like four number of sinks, which is this one, 4, and then they have like five number of sources, which is this one, and then each of these.
I believe this Excel file is shared in the ULEX. I think Paul can download it from the ULEX.
Oh yeah. Oh, okay. Very good.
Yeah.
So this is then the data that we have. Yeah. You can see all of these inputs, because this is all you calculated that already. The flow rate, and then the percentage of volume. and this one as well, the flow rate and then the percentage of volume. So this one you typically like use, let's see, I'll just cut this so that we know. Right, so say now, for example, this is an optimum value already. I mean, this is the result, and then you can see the cumulative hydrogen surplus. It's like 0 over here. So in the concentrations of this is concentration of 70%, concentration of 70%. And then if you go to the original case, is then if we plot this and that to make the two composite curves, the sink composite curves and then the source composite curve, we have this one. So we have the sink, and so we can make it like 1, yeah, 1, because it's nothing goes more than 1 because it's purity. So you can see now the source is then the bold lines. So this one is source. So as I mentioned, is then the 99%, the 99% of this guy, the source stream, the 99%, and then it goes. We have 1, 2, 3, 4, 5 of sources, which is in this case 5 of sources. And then the demand is 1, 2, 3, 4 stairs, 4 steps. So the 4 steps of sinks, the demand, yeah, and just to make it consistent, because this is what people have been doing. So if you so sink is then demand, yeah, because this is your source in demand, and then you get confused maybe with then the sink. Just to make it so, source is then sink is then the demand. So we have so this then the resulting of having this 237 something, because this is then the very strange number. This is the one that we want to minimize in such a way that that we have this kind of curve, and if we add these two together, we will have this hydrogen surplus thing graph, and you can see to then also y 1.2, I don't know, 1.2. So you can then see. So you can see this is then the resulting composite curves for the source and demand, where we have like from 0.7, like I mentioned to you, so 0.7 until 0.75, so which is in this case from this data, so they plotted here. So we have like the 0 0 point, it's on the 0 flow rate. So if you can see now it is now 237 something. So if we put like 250, maybe 300, right? So if you have like a 300 flow rate of 300 mole per second of hydrogen stream, you can see that the so it moves to the right, you can see, and this also moves to the right state now, right? So you have like a 300, and then everything goes to the right. Yeah, it's recalculated. But then if you put like so that means in this case nothing is then touching, apart from this line. Nothing is then touching the x equals to 0 line. So this means theoretically we can still reduce the amount of hydrogen required. So shall we then reduce it to 250, for example, and then you can see it moves to the left a little bit, but then you can still see there's none of this is then touching the 0 I mean the x equals to 0 line, and then this moves to the left a little bit, yeah. And if you put like okay, now I don't know, maybe 225, 25, and then in this case you have something like that. So this part goes to the left of x equals to 0. So this is also not this is not feasible. Yeah, this is not okay, because apparently we will need more hydrogen than 225. So this then how it moves around, and then what this Excel tool has done, and then as they say, we need to minimize this, make it as 0. So if you look into here, so we have to put this equals to 0. So we go to the I think it's in developer, right? No, all data. So we go to the what if analysis and then goal seek, And then you can say, well, I want to minimize this. I mean to minimize this. I want to make this into 0, because this one -3 is here. Is -3. -3 is here. Is that it? -3. So we want to put this, because this guy is then the closest to the x equals to 0. So you want to put this, push it to the right a little bit. So we want to put the not solver cosec. So this one we want to make it into 0. What we change, we will then simply change the amount of hydrogen we require. So there. So we get the previous 237, which is this number. So 23796 something. Okay, 551. So we have this, and then you can get that one. So this answers the question is then how big is then the hydrogen plant that we want to or how big is then the hydrogen fluoride that we can use to supply that we have to supply to the plant. And then that's the first question. And then second question is then because you are now here, right? So this then the 70% is then the lowest concentrations that you have. So here you can then say, okay, now I can also put the PSA to get some of these streams and then put it there in such a way that you can then how do you call it, reduce even further the this hydrogen plant, so to say. Okay, how do you do that? It's about 4. I think I will give you this, and then you will have to think. Yeah, but I will give you a hint. That means you can then say you can then add a new sources, right? For example, the PSA sources, and then you can then fix this to because this is then the hydrogen plant, right? Okay, we'll do that. Yeah, we have still half an hour to go because before we do this. How do we do this? Okay, anyhow, you save this, obviously. You save this somewhere in my, for example, in this case, in desktop, for example. I don't know. Desktop.
So basically, this pinch basis is exactly the same like heat integration, right?
Yeah, it's basically the same concept. All this pinch is the same concept.
And it is possible also to check by hand.
Yeah.
But long.
Yes, yes. It is possible to use by hand, and then that's why they use this tool. The same like a heat integration, you can calculate that with. So this basically, if you see heat integration, this is then what they call like transshipment or problem table algorithm. So this is then the problem table algorithm. Yeah, they use problem table algorithm, and then
But here I think you missed one thing, like for example, pinch point, right? That one also, if they don't learn heat integrations, they might not understand why we need to put 0 at that point, because actually that point is this pinch point, right?
Yeah, I think I mentioned this then in this hydrogen pinch, this is then the pinch point location, in such a way that I think you mentioned that they calculate in the problem table algorithm. I don't want to discuss this, but anyhow, in problem table algorithm, we need to make sure that this one is 0. So this one is 0. Up to you how you want to do that. But in this particular case, they make it already in such a way that if we can just simply find a goal seek over here to the lowest value of x in such a way that all of them, this one is then 0. So this guy is then the cumulative is basically 0. Yeah, so it really resembles the problem table algorithm. Now what I want to show you is that you can then you have to rewrite this. Yeah, I mean the save this, and then I want to copy this number. Okay. Okay, let's see. Now, if we have like a PSA, for example, yeah, I don't know. Let's see if this works. So I want to have, so that means we have like a 5 streams plus 1, right? So 6. So 6. Initialize this because we need to have that 6 streams. Yeah. So now it's a bit complicated, right? Okay, just simply copy paste 1 minute. Okay, simply copy paste this hydrogen pinch, right? Hydrogen pinch. And the 2. I think we have the 2. 1 minute, because I have to be safe as this. It's hydrogen pinch. Go on. Voila. So I can then copy paste this. Copy paste. Let me know if you cannot understand what I'm doing. Yeah? What I'm now trying to do is that we had like, I'll repeat this again. So in this case, we have answered the question on how much is then the hydrogen, the pure hydrogen flow rate, which is then this number 2, 3, 4 mole per second. This is then the amount of hydrogen flow rate minimum from the hydrogen plant, so to say. So suppose that we want to minimize these hydrogen imports from the hydrogen plant. So we will then buy like a PSA unit, for example. How big is that PSA unit? Yeah. So that's the question, the second question. Yeah, the second question. How big is then the PSA unit? That's the second question. And then you can then say we copy again the same because it's same users. Hydrogen pinch. Not this one. Ah, 1 minute. I'm clicking too many. Hydrogen pinch. Oh, this one. And then we have the so we have it's more like an iterative in this case. So we have the for example. So we have, for example, yeah. So I have now here. These are the existing users, right? If you can tell. I would say if you can tell. So this is then the existing users, and then we have the hydrogen stream over here, right? The 99% hydrogen plant, for example, and this is 99%, and then this then PSA unit. So you can say, well, this is then because this we have to order these streams in such a way that it goes from the highest to the lowest in the hydrogen concentrations. So suppose assume now I can then build a PSA unit to produce for me like 95%. Just a number, yeah. I mean, if you have like a 80%, for example, or 90%, so that means this guy has to be number 2, and then that 90 or 80 should be 90 should be and the number 3. I think you get my point. So, for example, if we have like a hydrogen plant of I want to minimize this. Say for example, if I want to only use instead of 237, I want to limit that to 100, and then what would be then the how big is then the PSA? So we assume, for example, it's 1. Yeah, I don't know, since we don't know. So if you can then click analyze, it will then calculate for us this guy, the initial value, and then we can see the source and demand graph looks like this, and then the hydrogen surplus, everything is then negative. You can see negative. So we need a lot more hydrogen. Because we only supply 100 as the purest. So now we can then see, so if I understand this correctly, like what we saw, this guy, right, at the very, so this is the one that goes to the far left, so which is this one. So this far left, we have to put this into 0 in such a way that the whole graph moves to the right. See if I understand this. Then we go to the data analysis, goal seek, and I want to make this into 0. What do we change? I change the PSA plant, right? Because I limit myself to the hydrogen plant, so it has to be like 100. So how big is then the PSA given this concentration? There. So it looks like this, but then we can then see. So it's still something like that, and then it looks somewhere here. So it's minus 14. So that means I don't fully understand this. So if I go that one, so there has to be like a 0, and then I change this guy there. So now everything is then positive, and this is the only thing that is then equals to 0. And then if I see this surplus, now looks like this, which is then in this case it's okay. Yeah, so nothing is then the negative, so it's everything is okay, and then we can then say okay. So now instead of having so we need so in this case particularly we have hydrogen plant with only 100 mole per second, or we buy only 100 mole per second, but if we install PSA with this 180 mole per second of capacity, we can still live, I mean we can still run the plant. So we can then say, now we can then say, you can then argue or compare the cost. Compare the cost. So now, right? So you have a saving of hydrogen plant 137, right? So 137 is then your saving. So you can calculate how much that costs, and then that cost should be at least bigger, or at least the same, or it has to be bigger than the cost to build this PSA with this big at this concentration. Okay, so this concentration, product concentration for PSA with this fluoride. So instead of having 237, which is 100 plus 137, you can have hydrogen band of 100 and then 179 of PSA unit at these lower concentrations. And then with this exercise, you could then imagine if we have a lower PSA concentration, for example, 93 or 91 or 80, you will need a lot more PSA. Yeah, you can imagine. If not, then you can then use this and then to get, I mean, so that you can understand. Sorry, before I close, do you have any questions? GDP, image original. Do you have any question on this? No? Yeah, okay. No, then fine. Now we move on. So this is then the Excel tool that people have developed, and then so then you can ask me, okay, so where is then the optimization? Huh? This tool is in fact an optimization in this case, because we want to minimize the amount of hydrogen. So minimization is the optimization. So you can use that as an argument. But then there is another way. There's another way. So our way is so now in this case, so this is like a simple case study, right? Simple case study. So you have like can you access? Now we can you access this tool? Because I think Seth mentioned that this tool has been in that you will learn. Can you access this? If you can access this and then you have it at your hand now, if you have it, maybe you can do this. You can spend like, I don't know, maybe 2-3 minutes on this, because we make it as simple as possible. So we have like a demand like this, and then this is then the source. Yeah, you don't have to think about because we don't have the purge and then stuff, so it's as simple as this one. So we have a demand and we have the source. So how much is then how big is then how much is then the coming here? Well, typically if you don't know the story that we have been discussing so far until 17 slides, you would then say, well, we only need this hydrogen plant to be 600 plus 400, so 1000 million scavs. So we need to have 1000 million scavs of hydrogen plant to be consumed by process A and process B. That's the typical answer. But then you have this knowledge already, and then you know how to do that with this Excel tool. So you should then be able to calculate how much is then the actual plant that we require. So you could do this. I think I will do this and then do the show you the linear programming, and then we can then call it a day. So okay, now I want to save this and then save as One. I don't know. Yeah, so then you can say, okay, now I have now two demands, right? And then the two plus one thing, plus one source, two plus one, so three sources. So two demand and three sources, two demand and three sources, two demand, and three sources, right? So you initialize, yeah. And then yeah, we don't know how big, I mean, how much, how pure is this concentration of hydrogen, but we can say, well, it's a hydrogen plant, so it's 99%, for example. And then you can put one, I don't know, hydrogen plant. And then process A, process B, copy, yeah, so lazy, oh, paste. Now the demand is then to 400, and then 90.8, right? And then B is then 600, and then 87.6. And process A is the sources is then 350 and 91%, and then 500. This is 85%. Okay, so and then you click analyze, and it will then calculate for you the thing. And then last time we yeah, I did it wrong, so I tried to minimize this, but apparently I can go, if I go straight to here. Let's see. So so make this guy equals to 0 by changing how much is then the hydrogen plant, right? There. So now you can see that one. Looks very strange. I don't know why it looks very strange. So in this case, we need to have 192 of hydrogen stream as opposed to 400 plus 600. Okay, you can see that. So that's then basically the target. But then how is that possible, right? How is that possible? How is that possible? I mean, oh, sorry, close this. This is the master. How is this possible? Right, I mean, because while we need 400 and 600, and we have only like a hydrogen plant of 192, so we need 1000, and we supply only like 200, so to say. So where is then the remaining 800 coming from? So to answer for that, we will then have to develop the linear mathematical model for this. So that linear mathematical model is something like this. What happened? Swap delta. Okay. So it's basically yeah, I'll show you notepad paint. Okay. So we have, oh yeah, I will show you this one first. So we have source A and then the sink A, yeah, just a notation. So we have this source A and sink A, and then this source A, which is this, it can be recycled here, and then it can also be put it over there, yeah. So this source A, it has two destinations. It has three destinations basically. It can go to process A and process B. These two are favorable routes, or it can also go to the fuel, yeah. So recycled one, reused to B, 2, and then fuel to 3, as it is now. The same goes with this stream. So it can be reused to A or recycled to B, and then goes to fuel. There are 3. While hydrogen plant, it is we have to send it only to process A and process B, right? So we cannot send it to the fuel. So so this is what we call this whole possible combinations is something that we call superstructure. Yeah, superstructure. So this is then the superstructure. If I draw it, something like this. So we have hydrogen, we have A, and we have B. So this is what we call source, and we have demands, and we have A, we have B, and then we have fuel, right? So I don't. Okay, anyhow. So this A can go to A, it can go to B, and it can go to fuel, right? And then these sources we call it I. This demands we call it J. Okay, so this we can say, well, this is S hydrogen, and then this is then S A subscript A, and then S B. Yeah, you with me so far, right? And then this one we can call it like a demand A, and then demand B as a notation, and then demand F, for example. Yeah. Um, and we can say for every A can go to this flow, for flow A to A, right? So this then flow from A to A, and this one is also from flow from A to B. Okay, because it's from A to B, and this one is then from flow of from A to fuel, which is unbearable. Um, right? So this one. So you can then generalize this to become FA, because the whole flow rate of A, it goes from source A, it goes back to A, recycle, or it goes to B, reuse, or it goes to fuel, wasted. So total flow of A, FA equals to FAA plus FAB plus FAF. So you can then say all of this is then summation of F A to J, and then from J equals to 1, or you can just put J here. Yeah. So all of these three, A to J, because this demand is then J. dA is then dJ equals to A. So this is basically then dJ equals to A. Right? And then you can then further generalize this, because you will then do for every, for A, you will do for B as well, because B then goes to here. There's an option. There's also go to here, and then there's also go to there. So there are three options as well for B. And then hydrogen, you can then as well, I can put it over here, I can put it over there. If I'm being so stupid, I can also put it over here. So let it be. Yeah, so because then we can then generalize it further. So for every F, right, because this is A is then I, so Fi equals to summation of J, this is then Fij. Yeah, okay, you got that? So this is then the general formula. And then the same goes with the demand. So for example, look at A for example. So the streams that goes to A comes from the hydrogen, right? So this is then F hydrogen A, and then this line as well, which is then FAA, and then another line here, which is then FBA, right? So FA in this case is FA is then demand, which is then J, yeah, equals to F hydrogen to A, and then plus F A to A, which is then recycle, and then plus FBA, which is then reuse. So then the same with the same logic, you can then generalize this into F. This one is then I, because hydrogen, and then A and then B, they are all coming from the I thingy. So I and then A, right? So you sum all of this. So you sum all of the I, And then you can then also generalize this, because you are not doing this only for A, you'll be doing this for A, B, and then fuel as well. Well, fuel we can leave it, but nonetheless, so then it means you can have like Fj, because all this is then J. Fj equals to sigma is then I Fi J. Okay, so there's these two. This is what we call like a source limitation or source mass balance, and then this then the sink mass balance or the demand mass balance. This is basically what is meant by this guy, these two. Now you understand, I hope. This one and that one. And then how about this? This is about the hydrogen flow rate. Okay, so the hydrogen flow rate is that instead of only like this, then the flow rate, as I told you. What is that paint? So we have also like hydrogen flow rate, right? So this then the flow balance, and then we have the hydrogen balance, which is then we know what is then being required here, right? Because this is then the demand. So demand, we have the flow rate, and then we have the concentration. So you can then say, okay, I want to have, so for every A, so flow rate A times the concentrations of hydrogen in A, it has to be equals to, then you can then use this, all of this, because what is going to A is then the all of these streams, right? So then this is then multiplied with so this then F hydrogen to A times concentrations of hydrogen in hydrogen plus Fa and A multiplied with the concentrations of this is the sources, the sources of A, and then plus the Ba times the concentrations of B. So then you can then say, so this is then J, right? So Fj times Zj has to equals to F sigma. This is then the I, and then the Zi, and then I. Okay. So this equation is then basically this equation, right? So which flow rate to so I forgot to put the J. So I forgot to put the J. See, yeah. So this sink is then for every J. So for every J, this J and then that J, and then I put Z here as opposed to Y, but you get the point. It's the same thing. So then summation of I over here is then I, and then this then the Zi, the concentration of I, and then the stream is then Ij, Ij. So this one I forgot to put because yeah, because this I is then the hydrogen, and then the A, and then the B, and then comma, and then J is what we have, for every J. So these are the three mass balance equation that is required to solve this in linear programming. So these are all linear, and then we can then add the objective function. So like can add the objective function. Can I make it? Okay, so the objective functions, obviously we want to minimize these, right? This and this and this. So these three streams, we want to minimize this. So total flow hydrogen of hydrogen equals to FH2A plus FH2B plus FH2 fuel. So this is then the equals to sigma F hydrogen to J. This is then summation of J. So we want to minimize this, right? So we want to minimize this hydrogen consumption, right? Think right after this we'll then stop. Okay. Anyhow, don't know why. Nonetheless, so that's then the objective function. So I make this into an Excel. You can make it yourself, because this one I'm not going to share with you. But I don't know if I've shared this, but nonetheless, let me know. If I haven't, then it's good. If I have, then it's fine. because we have learned this in the second day, right? The linear programming. So what I put is that what we don't know. So what we don't know. So what we don't know is then the whole thing over here, right? The amount of hydrogen fluoride that goes from A to B to fuel, from B to A to B to fuel, from hydrogen to A to B to fuel. So all of this we don't know. So what I make is then I put it over here, for example, in this case. So I have fresh hydrogen, it goes to demand, and then it goes to demand 2. Source 1, it goes to demand 1, it goes to demand 2 as a recycle, this one as a reuse. Source 2 is then as the demand 1 as a reuse, and then source 2 as to demand 2 as a recycle. Yeah, so these gray boxes are like the amount of flow rate which we don't know yet at the beginning. So these results are simply the results. And then I have this source restriction. Oh, I have the 1 minute. I have this one. Yeah, I have this one. Right. So this is basically the Fij, which we don't know, and then this is then the source restriction, which is then for every I, Fi, it has to go. I mean, it's the summation of I to every j, which is this one. Yeah, I mentioned to you, which is this one. For every I. So that's the source restriction, and so we also have a demand restriction of the sink. So whatever comes in, it has to be equals to what is required, which is this one. And then this then the hydrogen balance, which is this one, which is now being closed. I don't know. So that one, that's the hydrogen balance. And then you can do this whole calculations and blah 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 blah. And obviously you will need to input the data. So I put all of these calculations in it. So but you get the point. Yeah, you have the source restrictions and the demand restrictions, and then the hydrogen balance. What we need to find out is this guy. So we don't know this one. And then we know that. Oh, 1 minute. I'll make it bigger. So we have the demand data, the flow rate, and then the hydrogen required. We have calculated that already, and then the hydrogen requirement. So this one, the sources, and then the concentrations. But we simply don't know how much is then the hydrogen flow rate. This is something that we want to find out. Okay, and then based on this mathematics, and we put it into here. And where is my solver data solver? So here, so my objective is then this I16, which is then the hydrogen supply. So I want to minimize that. Yeah, what am I changing? G3 until H5, so somewhere here. So G3 until H5 over here. So because we need to know how much fresh to demand, we need to know how much fresh to demand 2, from source 1 to demand 1, from source 1 to demand 2, and so on and so forth. We need to know how much is then each recycled or reused, and then the constraints are simply this one is then the R17 equals to S17, R17. Okay, so this one. So this one 17, 17, 18, 18 is then basically this one, which is the zinc mass balance. And I have also the T and then U, T and then U 17 and then 18, T and U 17 and 18. And this is then the hydrogen mass balance. And then I have the supply restriction. So I and Nk. So this one has to be lower than that one. This one has to be lower than that one, because why is that so? Because the source you have like a 350, right? So you can use all of them 350, or you can use a lot lower than 350, but you cannot use 351 because there's no such thing. So you're limited by 350. The same goes to source 2. So we have the zinc requirement, the hydrogen requirement, and then the source restriction. So what we need to do is then to find the how much is then each. So I don't know why this then linear, and then So I put this G3 and H5, all of this lower than zero, bigger than zero, because it has to be a positive flow rate, and then we click solve. And then we have the result, which is then here, and then so in this case, the fresh hydrogen goes to demand 182, and then the source 1 goes to demand 1, which is then the recycle. So 93% and 93%, 93 million scuffy then 93 million scuffy then recycled to demand 1, but then the 256 is then the reuse to demand 2. The same goes with the source to demand 1, reuse 123, and then the recycled back is then 343. Okay, so for demand 1, it receives 183 of fresh hydrogen. This one is then recycled. This is then the reuse from source 2. And then for demand 2, we have no fresh, but we have reused from source 1, and then we have recycled. So you can play around. Yeah, say for example, you say, well, I don't want to have like a recycle, so that means you can then remove source 1, demand 1, so you remove G4 from the equations, and you can also remove H5 from the equations, right? So you can then play around and then see how much is then the corresponding hydrogen required for every analysis that you do. Okay, so here we see these are the results. Let's see how much was that. This one, was it this one? Right, so 400, 92.8, 92.8, 637, 637, and then 99%, 91, 85, 350, 500, and then this tool says, well, we need to have 192, and then our linear programming says it's 182. So who's right and wrong? I will leave you to decide, and that will be then your homework. To know who's right and wrong, you can then simply recalculate this, manually, and then you will see which one is then the right and wrong. Maybe we did something wrong here. I am not really sure, but it has to be. I mean, the goal is that this number is 192 something. It has to be the same as 182, right? The inlet is then the same. 400, 600, this one is then 99, right? Because this is very important. 99, 91, 85, 750. I don't know what happens. Something that I will leave you to it. Check which one is then correct, the 182 or 192. And then because I'm not giving you this, so I hope that you can then based on the what was it again? Based on the based on the data here, and then the formulations over here, and then the objective function, which I did not write somehow. You can then develop this on your own in Excel, the way that we did it last time, so that you can then come to your own conclusion. So I put the results over here. So it's 182, right? So 182. So in this case, it's 90 to demand 1, and then 92.8 to demand 2. So different versions of solver solve it differently, because we know that I think I explained briefly in the linear programming. So you can have multiple answer, but then the multiple combinations, but then the total answer, the objective function, which is in this case the amount of fresh hydrogen, it should be the same. So in this case, it's at 182.9, which is the same, 182.9. Just that in this case, it goes ultimately all to demand 1. Okay, while in here you have like split somehow. I don't know why. Okay, and then this one is then the results. So this then the base case, the current point, and then the base case will then say, okay, some guy will say we will need to have like 1,000 million scuffs of hydrogen plants, 99%, and then you can come and challenge him, say no, we only need like 183. Okay, if you want 183 or 200, maximum 200 million scuff of hydrogen plant at 99%. And then you can then propose this as your recommendation. If this recycle and then this reuse and then that recycle is allowed, yeah. And if not, and then you know what to do. I showed you already. So you can then remove this and then remove that from the equations. Say for example, no recycle is allowed, and then you can rerun that and then get how much is then the reuse. And then if you say that, well, I can only reuse A because A is the 91%, I cannot reuse B because B is too dirty, for example. And then there is no recycle and then there is no reuse for B. So all of this B, so all of this stream from B is all gone. Yes, you set it to 0 or you don't put it into the equations. So then you can then say, okay, if that is then the case, how much is then the required hydrogen plant for that specific case? So these are the things that you can then play around and analyze it and then make it like a different cases so that they can have a comparison. So you can have multiple options from which you can then compare and then propose. I will then, we don't have much time. We don't have time even to do, if, say, for example, well, hydrogen is not only like a mass balance, yeah, the pressure constraint as well. So this will be then something that you can read. Yeah, I put it here, but you can read it as well in the 3 articles that I mentioned over here. So you can read them and then see how they formulate that. Before we close, do you have any questions? So this one you can read it on your own, yeah. But because my goal is then to think, yeah, at least so you know already how to find the minimum amount of hydrogen. Well, you know already where hydrogen is being consumed, where hydrogen is being produced, and then what is then the typical flow diagram for these hydrogen consumers. And then from this information, then you can then calculate how much is then actually hydrogen flow rate and then hydrogen concentrations are needed. And then from this information, then you can then map this into the superstructure in such a way that you can tell what is the minimum hydrogen that you actually need, number one. And then number two is that if you have like a hydrogen purifier for the PSA, how big is that? And then what is then the concentration that you have to have? And then lastly is that if we allow some reuse or recycle of these hydrogen streams, what is then the configuration? So I think you have seen this, you have seen them all. If not, then let me know. The recording will be there, and we have our WhatsApp group. But nonetheless, before we close, do you have any question?
Maybe I take this opportunity to remind about make some announcement regarding the test two. Is it okay?
Yeah, fine.
So the test will be next week, 9:30 until 11:30. You will find the questions in the UX. I think as usual.